I am very excited to introduce Tycho because, well, first he's a legit security person, and the reason why I know that is that he doesn't have a Twitter account, and I searched high and low and I couldn't find one. So it's kind of annoying when you are doing this marketing thing, when you're trying to tweet somebody's talk and they don't have a Twitter account. You're like, what name should I? Anyway, he's also one of our resident kernel experts, and since the very early days of Docker and back then .cloud, it was a thing that I was often missing a lot. It's to have somebody that you can go to and ask your tricky kernel questions. And unfortunately, for a while, that person was me, and that was not good for the company, because usually my answer would be, give me 1 week in a cave with Elixir, like the Linux source code cross-referencing tool, and then I will come up with an answer that you don't like, and I won't be even sure about what I'm telling you. So it's good that we have now people who really know what they do with the kernel, and that's really necessary for everything about containers and security. So without further ado, I'm introducing somebody who's gonna tell you about new stuff upcoming to the kernel, stuff that might land soon, stuff that might land never, but new stuff anyway. Tycho, please clap him.
Check 1 2, mic check. We're live. Cool. So the first thing that I should disclaimer: this talk is basically just going to be a brain dump of everything that's happening in my head about the kernel and what's going on. This is a picture of me with a very bad haircut. I did not do a lot of the work you're about to see. I did do some of the work, but this is mostly just an overview of what's going on in the kernel. I'll try and point out who's done what work at what times, but you should know that other than the last thing that we'll talk about, I have not done any of this work. It's just part of my job at Docker to keep on top of these things. And the last thing is, Jerome mentioned it, the kernel development process takes a while, and with the exception of one thing that I'll talk about in this talk, everything is not as yet merged. So it's all subject to change, and people, you may wonder, how long is this going to take? When can I use this? And the answer is probably sometime in the next year. But don't quote me on that. This is a, it's a process, and you sort of have to go through it. So the first sort of section of kernel-related stuff that I want to talk about is specifically container-related. So there's a lot of other things happening in the kernel, drivers and whatnot, but containers is definitely a very active area of development. And in particular, what we look at when we talk about doing kernel development around containers is basically adding namespaces to things. So there's a subsystem of the kernel called IMA, or IMA. People pronounce it both ways. And what it does is it's an in-kernel protection against unauthorized user space file modification. So what that means is the kernel will actually forbid you from opening a file if somebody else has modified it out from under you. And so the way that works is you're in user space and you want to open some file, and that syscall goes into the kernel, and the kernel will actually look at the extended attribute, some security special extended attribute that describes the file in some way. So you can set a hash on the file, and if the file is updated but the hash doesn't match, or you can actually, in some cases, sign the files as well using EVM, which is another part of this kernel subsystem. You can actually sign the file and load in a key to the kernel to say these files signed by this key are valid. And then if either of those fails, if the hash doesn't match or the signature doesn't match, you'll get an EPRM from the operating system. So user space is not even able to open files that have been tampered with in some way. And so what an IMA policy looks like is something like this. So there's a file in syskernel security policy, and you dump some policy text in there. So this is an example policy for proc, and then example one for X4 as well. You want to measure stuff but you don't, you want to maybe only check files that are owned by the root user or things like that. And then the section at the bottom there is this is a kernel command line parameter. So this is how you enable or disable IMA. So in particular, there's different modes. The default is off, which is you guys are all currently using IMA in the off mode. Congratulations. There's the enforce mode, which is the mode I described before, where it does the permissions checks and then gives you an EPERM if the file is invalid. And then there's the fix mode, which is, you may be wondering, well, how do I set these hashes? And in enforce mode, you're not allowed to accept the security.ima extended attributes at all. But in fix mode, you're allowed to update them. So the idea there is if you have some files that are going to change, you reboot, update all the hashes, and then reboot again back into enforce mode. And now the kernel no longer allows you to set those extended attributes. So if you're thinking reboot, you're correct. Hold on to that thought. Another thing that IMA actually allows you to do is use the TPM. So this is just the Wikipedia thing for TPM. But over here in the corner, you see two interesting pieces, which are attestation keys and the platform configuration registers, which is like a terrible name. But it basically is just an accumulator. And so IMA, you can actually load in a remote attestation key, and you can accumulate a hash of all the files that you previously opened. And then you can actually, using this technology, remotely attest that all of the files that this machine has opened are valid. They satisfied the extended attribute or whatever. So cool stuff. But anyway, the reason we're interested in it is namespacing. So one of the problems is the policy is global. There's just that one file. You have to reboot to switch modes, which is terrible in a microservice world. Every time you spawn a container, you don't have to reboot the whole box. That's a bad plan. So some open questions are which namespace to pin on. So we probably don't want to add a new clone flag, like a clone IMA namespace flag. But since it relates to files, maybe we should just pin this policy coordination to the mount namespace, because mount's related to files. The problem with that is that the mount namespace is not hierarchical. And what that means is when you unshare a mount namespace, it keeps no record of its parent pointer. And so, for example, if you're in a container and you have some policy that is being enforced, as soon as you unshare, that policy may go away unless you do something clever about policy propagation or something like that. And so this is the discussion that's ongoing. Another option is to pin it directly to the user namespace. The user's namespace is hierarchical, but there's a host of other problems with that. Here's an LKML thread, one of the most recent ones, but there's been several about what does this look like, and some discussions. So the next kernel subsystem I want to talk about is Audit. So Audit is much like the tale of Hansel and Gretel. It's sort of a way that the kernel can leave you breadcrumbs about what has happened in user space. So in particular, here's a sample audit log, and this is, I have some publicly facing VM on the cloud somewhere, and here's somebody who's trying to brute force it through SSH. So ban whatever this IP address is from your SSH logs, because it's probably a bad guy. But anyway, this is the sample of an audit log. So these are the sorts of things. Audit can actually log individual sys calls. So if you, for example, are interested in every time your container does a ptrace or something like that, it can log when files are open. It can log all sorts of interesting events. And Audit, you notice the first two bullet points here are the same, has basically the same problem. So you don't necessarily want to create a new audit namespace. Audit is designed so that administrators can figure out what happened. And so if you unshare and you pin it to the wrong namespace and it's not hierarchical, the container, like all an attacker would have to do is unshare their namespace, detach from the audit logging that is currently happening, and now they just do their nefarious stuff and you have no logs of it. So clearly that's a very bad thing in the case of Audit. The way that they're currently thinking about solving this, and here's two RFCs for from Richard Guy Briggs, who's the audit maintainer, about what to do about this. And their current proposal is just to create a label. So it's totally not used by the kernel at all. It's just user space can say, hey, I'm running under this label. And then they add a new capability that allows you to change the audit label. And then when a task forks or some event happens, that label is propagated, and the only way that it's allowed to be changed is if you have this capability. Again, there's some pushback and feedback on that, so check out those threads if you're interested in this. But the core of these problems is really that there is no struct container in the kernel. So if you're familiar with some of those super old talks on containers, there's a guy named Serge Hallen who did a lot of this work, and he says that containers are user space fiction. There's no such thing as a container in the kernel. There's no object that tracks this, and that's why the audit and IMA people are having such a problem figuring this out, is because what a container means to Docker is maybe different than what a container means to OpenVZ, which is different than what a container means to the Kubernetes people. Sometimes you want to share namespaces, sometimes you don't. Even Docker allows you to share namespace. So what that all means is sort of in question. And David Howells, I think it was maybe 6 months ago, sent this patch series to introduce a concept of a struct container to the kernel. And so what that looks like is it would basically introduce another system call that from user space you would call, you'd say container creates, here's a name, and here's the flags. And I think flags in this case would be, these are the namespaces I want to unshare or whatever. And then, the rest of it looks like a fairly nice API. So if I want to do a mount inside the container, what I do is I pass it the container FD and then the same mount flags as before, the source, the target, file system type, mount flags, all that good stuff. I could potentially change my current task's route to the container file descriptor. I can do make dir@, make node@. You may be thinking, well, we can already do all this stuff with the current API, and that is absolutely true. And sort of one of the reasons that I'm not completely convinced something like this will go in. And in particular, it's not just those things that I listed before. It's, bind mounts, open container sockets, fork into container. This would replace clone. Waiting on a container. This would replace just wait ID, the system call. Add keys. He's got even more stuff in the series about device restriction, which we currently do with the devices C group. Supervising the container. I think this is effectively just send sigkill to the init task. Anyway, here's the link to the thread. There's a lot of discussion from a lot of people who have worked on the container APIs for the current container APIs for a long time. And a lot of people have problems with this, basically because one of the advantages of Linux containers is there's no struct container, and so you can implement it however is convenient or necessary for your particular application. So I think there's a lot of pushback on this this particular patch set, but it's worth noting that it does solve a real problem, which is the problem that Audit and IMA have that I described to you before, which is for subsystems that are trying to add some kind of namespacing, there's really not a clear way, not an easy way for a subsystem maintainer to do that. So the next topic is the LSMs. So the Linux security modules, which some of you may know and love, SE Linux or AppArmor. But there's a few others. SMAC is one done by a guy at Intel. Landlock is one that's not in tree yet, but I'll talk about a little bit later. Tomoyo and Yama, it basically just restricts ptrace. Sarah, there's some development going on to bring in some GR security and PAX features about page read-write execution protections there. But also, the LSM guys want to jump on the train too and namespace their things and their kernel subsystems. And this concept actually has been around for a while. They've been talking about this in various forms. This is all stacking, chaining, whatever the word you use for it. This is all kind of the same idea. And so this goes back to 2004 at least, was the earliest article I could find. And so you may be wondering, what does that actually mean? So for example, if I have a host that's an Ubuntu host, Ubuntu uses AppArmor. But inside my Ubuntu host, I maybe want to run a Red Hat container. Red Hat spends a lot of time writing SE Linux policies so that you don't have to. And maybe you want to use those. And maybe that Red Hat container then wants to spawn some sort of Android Samsung development environment, which uses SMAC. And so currently today, you just can't do this. There's no way for you to run an AppArmor policy on the host and inside the container run an SE Linux policy and again nest it. And that's this idea is, so if the Android VM or Android emulator thing had SMAC running and it tried to open a file, the definition of nesting, I think, as people are describing it more recently, is the SMAC policy would first be applied, then it would go down to the SE Linux policy, assuming that is satisfied, then it will go down to the AppArmor policy, and assuming that is satisfied, then the kernel would allow you to open that file descriptor. So that's sort of what this looks like, and it's worth noting that actually today you can do this with AppArmor. So if you run an Ubuntu on top of Ubuntu container or something, AppArmor has implemented their own in SecurityFS. If you look in syskernel security, AppArmor namespaces, there's a whole control directory there where you can echo stuff into certain files and create namespaces and things like that. So AppArmor currently supports something like this, but it's very AppArmor specific. It's their own sysfs, SecurityFS implementation. And actually, like a week ago, Stephen Smalley posted, he works for the NSA, by the way, he posted this patch set that he's apparently been incubating for a while. I was recently at Linux Security Summit, and there was not a meetup, but a Birds of a Feather session on this issue, and in particular, what are we going to do about this? And this is where Stephen Smalley said, well, actually, I've been doing the same thing that the AppArmor guys did, where you'll be able to nest SE Linux. If this gets merged and the AppArmor thing is merged, then it may be the case that the LSMs are just going to do their own thing. Each one is going to be separate, and so we'll have no real way to nest them. But the guy at Intel who does SMAC has also been working on this problem for, I don't know, the last 5 years or something at least. And he has a patch set where you can actually do what I described in this slide, where you can mix and match major LSMs. So the patches exist. It's still in development. Here's a link to one thread. But there's and I had the links before. There's a lot of work going on in that area. Another thing is the time namespace, and this is just we'd have a new time namespace, and the motivation for this is there's a few different reasons. The one that I can think of that has affected me is I used to work on live migration of containers, and the problem is, when you live migrate to a new host, it may have some different idea of what time it actually was, and you get some clock skew, and that could screw up applications. So another thing is databases. I guess Oracle DB on Linux for a while wanted to do a syscall to set the time, and if that failed, then it would just exit one and say, I can't work. So the workaround was to install a seccomp policy that just lied and said it succeeded. But it would be nice to solve this problem for real. The set of system calls is fairly small that it involves. It's just get set time of day. There's some other system calls here, and there's some files in proc. A few other places it expose. But in principle, it seems at least to be very easy. Except that it's not. And the reason it's not is something Liz gave a talk on earlier, which is the vDSO, which is Virtual Dynamic Shared Objects. And so if you're not familiar with this, you should go watch. She talks about it in a lot more detail. But basically, this is optimization to make frequent syscalls faster. So one of the motivations was, I think a while ago, Firefox had this problem where they were logging a lot of stuff, which is not necessarily a problem, except for they were prepending a timestamp to every log, and then every timestamp they would do a syscall to get the time. And the problem is, if you're logging lots of stuff, it's just thousands of syscalls going over and over again. And so it turns out if you turned off vDSO, I think I don't know if Firefox still has this problem, but it would basically just hang and be uncontrollably slow or unusably slow. So anyway, what vDSO does is it's a way to speed up system calls. And so the kernel basically injects some code into the task's address space, and your libc knows to look for that code to see, oh, hey, do I have vDSO support, and can I use it in particular to accelerate these system calls? And so what that looks like, the implementation is actually for like system calls like time is there's a shared page that's mapped into every task's address space. And this code that's injected knows where in memory that shared page is looked at. And then the kernel in the background has a task that runs periodically that updates the content of that page to say, here's what time it is, here's what time it is. And so the user space stuff, instead of trapping to the kernel, doing a bunch of stuff, and then trapping back to user space, the only thing that happens is you call into the user space code, it goes and looks at this specially mapped page, and then grabs the value from there, and then returns it to you. And so you don't have to trap to the kernel at all. And so that's very nice, except that it makes namespacing time quite difficult, because you have to deal. I don't know if you've ever looked at the implementation of this, but at least on x86, it involves like a lot of linker scripts and like other crazy stuff that you have to pass to GCC. And so it's probably possible, but there's a reason it's not super simple, I guess is the point. And this, I had a number of people talk to me about doing the time namespace at the recent Linux Security Summit, and probably this is one of the reasons that nobody's done it, is because you'd have to sit down and figure out this. So it's not impossible, just difficult. So I guess that's adding namespaces, container-focused stuff. There's also some just interesting security stuff that's happening in the world. And in particular, this is the one feature that's actually in the kernel that you can use today, so I'll demo that for you. This is a seccomp logging feature. First, I'm running a 4.14 RC kernel from a few weeks ago. So this is, I think, will be in 4.14 when it comes out. And what I have here is a C program, so sorry if that scares you or offends you in some way. But this is just a C program, and I have a little a function here that filters syscalls just based on whatever number they are. And if this looks like a bunch of crazy macro terribleness, it is. But basically what this does is this is the actual eBPF bytecode. This is hand construction of the eBPF bytecode. And then what I'm doing is I install that via seccomp. And then down here I have just the entry point. And the child that will get forked that we're interested in, I'm going to filter the number, the syscall open, read, and close. And then I do some synchronization here, just basic. And then, so I open the file, I read a bunch of times from it in a loop, and then I close it. So that's useful information. And the magic part here is this part that I'm going to uncomment, which is this new flag, seccomp filter flag log. So you'll notice up here, my seccomp program itself has a seccomp ret log in it. And this basically means, this is almost like the strace version of seccomp. And I'm using log here just as an illustration, but in the past it was kind of difficult to reason about what happened when you have some closed source thing. Sometimes seccomp logs, you don't know where they go, and so it was difficult to say, oh my, the thing's dying, and this is the syscall filter that's screwing it up. So this kernel patch set is meant to address this. So just as an illustration, I'll make seccomp. Worth noting that I don't have a make file here. This is a trick a lot of people don't know. You can just use make, like I just did, even without a make file. They're called implicit targets, I think. So then if I run this thing, it did its thing, and just to remind you all that it read in a loop 10 times. But if I go look at the kernel log, I'm down here, and you can see here's my audit log, and the first thing is syscall2, which is open, and then you see, I guess I could do this manually. Down here, if you look in the middle there, you can see, or on the bottom line that's highlighted, the syscall is 0, and there's only one of those before we go to syscall 3. And so this is just an example of, your libc is not exactly a system call because I read from the file 10 times, but in fact what really happened is there was one read of, probably a page length, I think is how long libc caches. So just an interesting little tidbit. If you're using fopen and you're opening lots of little files, the buffering can possibly kill you. That's a problem that I have seen. So anyway, that's just a new feature in seccomp that is useful if you're having problems figuring out what seccomp policies to use or that sort of thing. You can use this feature to figure out exactly what is happening. So one issue is that seccomp can't dereference pointers, and what I mean by that is if I have a pointer to a file and I do the opening of that file, I will execute the kernel is not atomic. Syscalls are not atomic. So what happens is seccomp runs at the beginning of every syscall and says, "Okay, this is fine," and then it actually calls the real implementation of open, which goes through some VFS file path down to do dentry open. But then I could change the value of this. If some other thread in that task thread group changes this value, then after seccomp runs, it says, "Oh, it's okay," but there's this race condition where I change the value, and now there's a time of check, time of use issue, and so there's no way in the seccomp API to dereference pointers exactly because it's not safe to do. So what you'd really like to do is put something in DL entry open to determine whether or not this is going to work or whether or not this is allowed, because that's the place where the thing that's actually going to be opened. And so that's what Landlock is sort of doing. So this is there is a hook there. This is where all the LSMs hook in. So this is exactly the same. You can write an AppArmor path rule that says don't allow files at this path, and that's basically what it does here. Is it checks at this point. But the interesting thing about Landlock is that it's not just a rule. Landlock is an eBPF-based Linux security module, and eBPF, if you're not familiar, is basically a way that you can install arbitrary programs into the kernel. And so you can run a program in the kernel to decide whether or not an access is allowed, and it's a super interesting facility. Just to clarify here, the signature of security file open is it passes the actual file that's going to be open and the task current credentials, and in that struct file there's the actual inode that's going to be open. So then you can reason about exactly what user space is going to see, and you don't have to worry about race conditions. And so the fact that this is a programmable way to reason about exactly what user space is going to see is very exciting. And so this development is going on. I think I didn't put a link in here, but this has been around. The guy who's doing this is Michael Salan, and he works for some French national defense place. And so anyway, this has been around. There's like 6 versions of it out. It's currently under active development, but this is potentially very cool stuff. The next thing I'll talk about is Wireguard, which is something that's happening. I was going to do a Wireguard demo, but you basically just saw one if you were here for the last talk for Rolf and Justin. So I got a lot of stuff to talk about, so I'll just skip that. But Wireguard is a cool, simple, fast, modern VPN that allows for transparent encryption between endpoints. As Justin said, it's just a device. And so your application doesn't have to know anything about it at all. All it knows is I have a device which has some valid routes to who I want to talk to. And then below that, there's some magic to handle it in the kernel. Some interesting stats, vital stats about Wireguard. There's lots of other VPNs. Why do we need another one? Well, it turns out this one is quite small compared to more traditional things like IPsec or OpenVPN. So in theory, it should be much easier to audit. I think in practice it is as well. It's based on the noise protocol by Trevor Perrin, and it uses some ciphers. Please don't ask me about this. I'm not a cryptographer. I assume those are good, but the guy who wrote this is a smart guy. You should ask him instead. But worth noting is that there is no cipher agility. So if one of these is broken, you have to upgrade all of your nodes at once. There's been a lot of attacks in like SSH, in the last 3 years or something, where you at some point you can say, hey, I want to use this insecure cipher, and SSH says okay, and that's just not allowed in Wireguard. So it alleviates this whole method of exploitation, but also makes it a huge pain if you want to change ciphers. So that's Wireguard in a nutshell. So the last thing I want to talk about is not necessarily features, but just hardening itself. And for those of you who have a keen eye, this is in fact a picture of Gordon, who is the mascot for Docker. This is the actual turtle that lives in the San Francisco office that you can go there and feed if you're so inclined. But the last point, or the last couple of things here, the kernel hardening is mainly done under the umbrella of the kernel self-protection project Upstream, which is about 12 organizations and 10 individuals working on 20 different hardening technologies. These are things like stuff that was cooked up by academics, which is the thing I'll talk about next, to attacks that are well known and have been defended against in out-of-tree patches like JR security and things for a long time. Case Cook did a great update on this at Linux Security Summit, where he goes through in great detail what everyone's working on, what the threats are, who's doing it. His slides are very good, and they're very readable even if you didn't see the talk. I think they were designed explicitly for that. So I encourage you to check that out. A lot of cool stuff happening here. But the last thing I'll talk about is specifically what I've been working on in the realm of kernel self-protection, which is something called exclusive page frame ownership. And so this was originally cooked up by some academics, and they coined the term ret to dir attacks, which stands for return to direct mapped memory. And the whole implementation is about 1,000 lines, and that it has some architecture-specific stuff because it needs to do manipulation of page tables and stuff by hand. But that's what this is, the statistics for, I think, V6, and I have posted, or I haven't posted V7 yet, but I will probably in the next 2 weeks. So just to kind of give you an idea of what this defends against, I'll just give you some basic information about how the memory management subsystem works in Linux. The subsystem is called MM. That's the directory it lives in. So anyway, typically when you allocate some memory on x86, you get a pointer that of the form 0x000 whatever. And that's the pointer that your user space code sees and uses and manipulates. And that's a virtual address, virtualized, and you can tell it's a user space pointer because the high order bits are all zeros. But the insight here is that actually points to some physical page, and the kernel has a direct map of all of the physical pages on the machine that it maps, and it keeps mapped forever. And the reason it does that is because you may be doing direct memory access, or there's a lot of reasons to have this around. But suffice it to say that there is a valid kernel pointer alias for this physical page. And if you look, the high order bits of the kernel pointer are all Fs. And so, so a classic attack looks like this, where you have this pattern exists a lot in the kernel, where there's like a structure that contains a bunch of function pointers, and they all implement that file. So, like your dev0, when the read thing for that just returns as many zeros as it possibly can. And so how files are implemented in the kernel are implemented with this pattern. There's a structure, and it has a pointer to some valid thing that implements the actual flush for that thing. But then if I want to attack the kernel, what I'll do is I'll write like a not real flush function, and in there I'll put the shellcode that is please give me root. And then what I do is I overwrite through some other attack. There was a recent attack in 4.13, the wait ID syscall. You could write arbitrarily to kernel memory. So these do exist. You just write over the kernel function pointer, and you say, hey, give me root. And the idea is if you know where this file operation struct lives, it's a lot easier than trying to figure out exactly where your dynamically allocated task struct lives for your tasks. You don't have to overwrite the creds yourself. You can just write this shellcode in. And so there's a lot of things that protect against this. The first implementation was uderef by Pax a long time ago, 15 years probably something. And then Intel has codified defending against this in Silicon via SMAP and SMEP. So this stands for supervisor mode execution protection. So that's the attack I just described. And then SMAP is access protection. So this is the kernel can't even read user space memory unless you twiddle some bits in the right order. And the way that these, and there's PXN on ARM as well. And the way that these work is they basically look, I pointed out that the low order bit or the high order bits for a user space pointer are zeros and the high order bits for kernel pointer are ones. And the way that these figure out whether an access is valid are they detect, are you in ring 0 or not? Are you trying to access a kernel with the right high order pointer with the right higher order bits set? And so you can see maybe where I'm going with this. So there, we have a direct map of a page, and we can allocate user space memory, and so we do the same thing. We allocate a user space pointer. We write the bad shellcode into that. And then instead of overriding the flush function with the bad user space pointer, we instead override it with the kernel pointer. And assuming we can compute that alias, which the academic paper showed you can do about 96% of the time, it's a little bit of guesswork, but through techniques like heap spraying and things like that, it's pretty easy to be successful at this attack. You can bypass all of these traditional protections, assuming you can you have arbitrary write access in the kernel, which is bad. And so this is what exclusive page frame ownership protects against. The idea is you just keep track of who owns a page, whether it's the kernel or a user space, and you map and unmap accordingly. And the reason that the kernel doesn't do this now is because it turns out it's extremely expensive, to the tune of 2.5 to 3x. But if you, I think somewhere, maybe I don't have. Anyway, if you Google XPFO and kernel hardening, you'll find my last set, and there's a bunch of discussion there about how to speed it up. So it's potentially enabling that this may not be as expensive as that someday. If you're interested in any of this, shout out just to some mailing lists where this stuff's happening. A lot of people don't know about the containers list in the Linux Foundation. A lot of the stuff I described in the first section of the talk happens there. Kernel hardening, a lot of the stuff I described in the last section of the talk happens there. Most of these subsystems do not have their own mailing list, but IMA does, so I just threw a link to that in. Check that out if you're at all interested. The first one is potentially the most relevant for this crowd. And with that, thank you, and I'll take some questions.
Hey. Thank you.
Yeah.
So when you were chatting a little bit about the container struct, I just wanted to ask a clarifying question.
Sure.
Read a little bit about the user namespace, and you described how it maintains a hierarchy. And then you also kind of had an addendum that you didn't dig into, where there's maybe potentially some other issues with pinning IMA, and audits to the user namespace. And then you also chatted about the LSM modules implementing their own namespacing.
Yep.
And so I'm not really familiar with this domain of problem solving in the kernel. Does the user namespace also have its own dedicated problem solving area in order to create that hierarchy without structs that are specific to these other namespaces?
So the hierarchical namespaces, this is defined in the namespace framework. So there are a few namespaces which are hierarchical. I think the process ID, user namespace, and C group namespace at least. There's probably some others as well. But so those and there's the kernel supports. It has function pointers and all the structs to do that resolution of hierarchy, and they're either defined or they're not. For namespaces that exist today, it's well defined whether I'm not sure if I'm answering your question.
It does, but I guess what puzzles me is that it doesn't seem like IMA is a namespace that's dependent on other things that would be in a container struct, and I'm kind of curious why that would be helpful. And same thing with auditing.
Sure.
Like, why wouldn't you just have that namespace be responsible for its own hierarchy?
So you could do that. Honestly, the practical reason is that there are no more bits left in the clone syscall. So we need a clone 2, and we have to migrate all of user space to using clone 2 in order to make that happen. But I think the reality is there are a lot of other things. There's certain files in proc and other little bits of things that are namespaced that are just sort of dependent on that, you know, like some existing namespace. It makes sense to just tie it to that. And I think in a lot of ways, the IMA namespace in particular does make sense to be tied to the mount namespace, assuming you can figure out what to do about when to unshare policy. So yes, we're out of bits in the clone syscall. That's a problem that's solvable on the 10-year time horizon. But the more, I think, the bigger issue is really not everything necessarily even needs its own namespace. So like I say, the IMA mount thing, that seems to be fairly highly correlated. It's just we haven't figured out exactly. There's some issues there. Does that maybe more?
It does. Thank you.
Okay.
Appreciate it.
Other questions? Anyone?
No other question. Going once, going twice. Thank you.
Yep.
So one more round of applause. And if you come up with more security questions, come and find him and ask him. Well, I mean, in all seriousness, when I was learning about kernel stuff, when I was trying to learn about kernel stuff, having someone you can ask questions to is super useful, especially having someone you can ask questions to without them being like, well, you obviously should read those 200 pages of source code, damn it, idiot. So, yeah, when you have somebody you can ask questions to, do it. One thing I forgot to mention is that there is a mobile app that you should use to leave reviews for the talks, especially like if you're still here, it's either that you fell asleep or that you enjoyed that talk. So please leave reviews on the talks, especially if you liked the talks, because then we use that to know what we should have for future DockerCons. And on that, I will see some of you maybe at 4:15, or that's 16:15 in normal time, and we will talk about serverless. Thank you.
All right.